Hi, I'm J Wildberger, and today we're looking at isometry groups of planar geometry in the context of a general dot product or inner product or symmetric bilinear form. And we're concentrating on our three familiar inner products coming from chromogeometry: the blue dot product, the red dot product, the green dot product. So let me just quickly remind you, we're in the plane. We've got vectors. Well, we have points, first of all, like A with the point 2, 1 in square brackets, B, 3, 3 in square brackets, and then the vector determined by those 2 points, V, given by round brackets 1, 2. Now, the bilinear form is usually associated to vectors. It inputs a pair of vectors and outputs a number. So the blue familiar dot product, AB dot CD, is AC plus BD. The red one is AC minus BD, and the green one is AD plus BC. And these three bilinear forms have these three matrices associated to them. This one, the blue one, is Euclidean familiar geometry, and these two, the red and the green, are both relativistic geometries. Okay, so what we want to do today is investigate isometries, that is, transformations of the plane that essentially maintain the structure given by these bilinear forms. This is a very powerful approach to geometry by investigating the transformations that leave invariant the quantities of interest that we're studying. And it's going to be quite interesting that ultimately these isometries have a pleasant group structure. And so we're sort of setting the stage for introducing group theoretical ideas into geometry and preparing also to go into higher dimensions where things get more complicated. Now, the basic metrical structure that comes from a dot product is that of quadrants. We have 2 points. The quadrants between those 2 points, usually denoted Q, is the quadrants of the vector from one to the other. And that's the dot product of the vector with itself. So vector dotted with vector gives quadrants, and that's how we measure the separation between 2 points. In familiar, sort of ordinary geometry, we would take a square root of a quadrant to get a so-called distance, but square roots are problematic logically and algebraically, so we prefer to stick with the quadrants as the fundamental measure of how far things are apart. And then we can observe that if we have a translation, so if we have a fixed vector, say V, and we decide to translate 2 points, A and B, by the vector V, to get, say, points A prime and B prime, then this transformation is what we might call an isometry. It's characterized by the property that it maintains quadrants. So the quadrants between A and B originally is the same as the quadrants of the points A prime, B prime that they are moved to. This is sort of the defining crucial property of an isometry, that if the quadrants between these 2 points is 7, and then you move them over here with respect to this isometry, the quadrants will still be 7. And that should be true for any 2 points in the plane. So what we're saying here is the fact that translation is an obvious isometry. We always have translation, and that's simply because the dot product of this vector with itself is the same as the dot product of this vector with itself, because these vectors are in fact the same vectors. Translating a vector doesn't change it. But what other kinds of isometries are there? That's where the story gets more interesting. All right, so now let's talk about how we represent isometries on the page and how we compose isometries. So here's the convention that we're going to use. A is a point, sigma is an isometry. A followed by sigma represents the effect of the isometry sigma on the point A. So this equation tells us that A is moved to the point A prime by the isometry sigma. This is convenient for us from a linear algebra point of view because we're going to represent points and vectors with row vectors typically. And then that will mean that we can use regular matrices to represent the isometries, and then this multiplication is just the usual multiplication between a vector and a matrix. Now if we have 2 isometries, say sigma 1 and sigma 2, Then we can define their product according to the following rule, that the way a product acts on a point A is simply to take the point A and act on it by sigma 1 first, and then act on that by sigma 2. So there's actual no change in order here, we're just changing where the brackets go. That makes it easier to remember. It's not too hard to convince yourself that if sigma 1 and sigma 2 are isometries, then this composite is also an isometry. If sigma 1 preserves quadrances and sigma 2 preserves quadrances, then doing one after the other will also preserve quadrances. Somewhat novel definition. Let's say that an isometry sigma is grounded precisely when sigma O equals O, where O is our origin. So if the origin is preserved under an isometry, we'll say the isometry is grounded. And then it's obvious that the composition of grounded isometries is grounded. And translations are typically not grounded because they always move points, at least if the vector that we're translating by is non-zero. But so the grounded isometries are kind of the opposite to, or complementary to, the translations. And they're the ones that we're particularly interested in. So let's start off with the simplest situation, the most familiar one, where we're talking about Euclidean geometry, the blue geometry, where the circles are the usual circles. And in that case, isometries that are grounded are reflections through lines in the origin and rotations. And in the usual classical treatment of rotations, especially, angles figure prominently. And you may have heard of things like SO2 or O2, the group of matrices of the form cos theta, sine theta, minus sine theta, cos theta. That kind of representation using angles is something we're going to avoid entirely here. So we're getting at the same picture, but through purely algebraic, through purely rational approach. Okay, so let's start with the blue situation. So familiar, and we're going to talk about grounded blue isometries. We want to know what are the possibilities for grounded blue isometries. So here's our plane. There's the unit circle where the points or vectors have quadrants 1. And we're interested in what kind of transformations could we have that preserve quadrants. Well, we're assuming that the isometry that we're interested in is grounded, so that the origin is sent to the origin. So this point is fixed. And now let's think about what happens to these 2 points, to the point 1, 0 and the point 0, 1. Okay, that one is fixed, we know. Let's just concentrate on what happens to those 2. Well, if the image of 1, 0 under the isometry that we're considering is, say, AB, then that has to lie on the circle x squared plus y squared equals 1, because the quadrants between O and this point is 1. And so when we apply the isometry, this point is not moving, so wherever this point goes to, it's got to go to another point on the circle. It still has to have quadrants from O. Okay, so that point AB has to lie on x squared plus y squared equals 1. And that's also the case for this other point, the point 0, 1, under the isometry. It also has to be sent to a point on the unit circle. But moreover, it has to be sent to a point that has the same relation to this one as these 2 originally had to themselves. So these 2 vectors here are perpendicular. Their dot product is 0. And the property of the quadrants means that dot products are also preserved. Okay, so that means that the image of this point has to be on the circle, but it has to be such that whatever line we join from the origin to it is perpendicular to this line joining the origin to the image of this one here. In other words, these 2 lines are perpendicular, so under an isometry, we're either going to get something like this, where they're still perpendicular, or something like this, where they're still perpendicular. So that means there's actually only 2 possibilities for these 2 points. It could be minus BA over here in the diagram, or it could be its negative B minus A, which is over here. And then a little bit of thought says that, well, that essentially captures all the possibilities here. There's only one possibility for where this point goes once we've specified it. And then there's only two possibilities for where this one goes. And then it turns out that knowing where those 3 points go is enough to determine the entire isometry. And it's then a linear transformation. So that when we work on vectors, we represent things in terms of vectors so we can use the language of linear algebra. Then the two possibilities for the isometry that we're considering are the following. Either xy is sent to the product of xy with the matrix A, B, B minus A, or it's sent to the product of the vector xy with the matrix A, B minus BA. So let me explain that. So let's look at this case here. This would be the case when the vector 1, 0, if you put in 1, 0 here, you're going to, after matrix multiplication, you're going to get that top row. So 1, 0 gets sent to AB. And the second vector is 0, 1. Product is that second row, B minus A. That would be that vector there. So this situation corresponds to the case when 1, 0 gets sent to that and 0, 1 gets sent to that. And this one similarly is just the case where the second vector goes to minus BA instead of B minus A. And those are the only two possibilities. Now it turns out that these geometrically are a reflection and a rotation respectively. And it's a great exercise to sort of remind yourself about how basic linear algebra things work, that yes, these really are rotations. So we're going to say a little bit more about this story, but I'd like to present today the picture showing the blue, red, and green isometries all at once, so you can have them in front of you and sort of see that they're all relatively comparable in a certain fashion. Okay, so here is the beginnings of the story for the blue isometries, and there's quite a lot more to say about this, and we will be talking more about that in subsequent videos. But this is at least a starting point of isolating what the isometries actually are. There are two kinds. There's reflections of this kind and rotations of this kind. They're all given by these 2 by 2 matrices acting on essentially vectors. That's in the case when the origin is fixed. So then we're in a sort of a situation where it's only described by vectors and what happens to them. Now at the level of vectors, the isometry property is most compactly stated in this way. If you have two vectors, u and v, you take their dot product, that's the same as what you get when you apply the isometry to both of the vectors. So u acted on by sigma, dot v acted on by sigma. So if that property holds for any two vectors, then also the quadrants property will automatically hold, because that's sort of just the case when u and v are equal. Okay, so how do we actually check that those matrices that we wrote down actually do have the isometry property? So that's a very elegant little computation, and it involves this crucial formula here. So I want to show you how that works, not just in the blue situation, but in a more general situation. Suppose we have a general dot product given by u dot v is u times m times v transpose. So you use a little 1 by 2 vector, a row vector. There's a 1 by 2, and there's a 2 by 1, and there's the m, it's the 2 by 2 symmetric matrix that represents the quadratic form. Well, then if we look at the left-hand side here, we're acting on u by multiplying by some sigma. We're acting on v by multiplying on some sigma. There's a transpose here. The way the transpose works is that the product v times sigma, take the transpose, you get the sigma transpose times v transpose, assuming that sigma is a matrix, which they are in these cases. And so we want that to be equal to the original u dot v. That's this condition here. Okay, so when is this going to be equal to this? When is this going to be equal to this? Well, these are almost the same. The u on the outside, the v transpose on the outside are the same. Here we have an m inside, and here we have a sigma m sigma transpose inside. So these two are going to be the same for all u and v, precisely when sigma m sigma transpose equals m. So that's the condition for a 2 by 2 matrix to represent an isometry. That if you take the matrix for the bilinear form, the symmetric matrix for the bilinear form, then sigma times m times sigma transpose ought to be m. So let's check that our reflections and rotations that we just got are indeed isometries for the blue dot product. The blue one is very simple because in that case the matrix M is just the 2 by 2 identity matrix. Okay, so when sigma was A, B, B minus A, then this left-hand side becomes that matrix times the identity times this thing's transpose. And what is the transpose of this? Well, it's the same thing as itself because this is a symmetric matrix in this case. The identity is just the identity, so it disappears from the matrix product. And we just really have the product of this with this. And that's a squared plus b squared. And then over here, ab minus ba, that's 0. Over here, ab minus ba, that's 0. And down here, b squared plus a squared, or a squared plus b squared. And remember, a and b were the coordinates of a point on the circle. So a squared plus b squared was equal to 1. That means what we're getting here is just the identity matrix. And yes, indeed, this matrix here does satisfy this equation where M is the identity matrix. And here's the corresponding formula for the rotation. AB minus BA times I times AB minus BA transpose. Now it's a little bit different because this is not symmetric, so its transpose is AB minus BA. Reflect along the diagonal. And then when we do this product, we get a squared plus b squared, 0, 0, and another b squared plus a squared, the same as we got over here. So yes, we're getting the identity again. So this is a straightforward way that allows us to check that any 2 by 2 matrix does represent an isometry with respect to a quadratic form or bilinear form given by some symmetric matrix M. So you have the symmetric matrix M, and then this is the condition for a 2 by 2 matrix to be an isometry with respect to that quadratic form. So now let's look at the story for the red geometry, which is a relativistic geometry, where we have a quadratic form x squared minus y squared instead of x squared plus y squared. We've seen in some previous videos that this story for circles is a little bit different. Now the quadrants q equals 1 circle is essentially the hyperbola x squared minus y squared equals 1. And we also have quadrants q equals minus 1 hyperbolas given by x squared minus y squared equals minus 1. We also have these two null lines that are at slope of 1 and minus 1. Okay, so we're interested in whether we can find isometries in this situation. We're interested in the transformations that preserve the bilinear form, which are grounded. So we're looking for grounded red isometries. It means the origin is fixed. So let's suppose that sigma is such a thing. And then let's look at what it might do to these two particular points, 1, 0 and 0, 1, the same 2 points we were considering previously in the blue case. Well, what's the quadrants of this point? Well, it lies on this hyperbola q equals 1. And that means that its image has to also lie on that point because we've said the origin is going to be fixed. So the quadrants between here and here, which is 1, has to be the same as the quadrants between here and wherever that point goes to, say AB. So if it goes to a point AB, then that has to lie on this hyperbola with equation x squared minus y squared equals 1. So suppose that's the case. Then what happens to this thing? Well, this is a quadrant of minus 1. And that's got to be preserved under the isometry. So this point has to go to some point over here. But it has to have a certain relation because in this original story, this vector and this vector are perpendicular. If you take the dot product between 1, 0 and 0, 1, you get 0 minus 0. So they're orthogonal. And that means that the image of these two vectors has to also be orthogonal under the red geometry. So if this point goes to the point AB, which we're assuming, then the possibilities for the image of this point, there's only 2 of them. One is BA, which is orthogonal to this, so this vector is perpendicular to that one. Or the other possibility is it's negative, minus B minus A. And I remind you, you can check perpendicularity because the dot product is BA minus AB, which is indeed 0. Geometrically, the perpendicularity is a reflection, a Euclidean reflection in this slope 1 line. These two are reflections of each other. All right, so those are the two possibilities. And then it's really the same kind of story as we had in the blue case, except the matrices are slightly different. We get two different possibilities. We could call them sigma and rho. We might put an R on top of them now because these are the red versions as opposed to the blue versions that we started with. So the red version is xy goes to xy times AB minus B minus A. That's the case when 1, 0 goes to AB and 0, 1 goes to minus B minus A. That turns out to be a reflection in this story. And the other one, the rho sub AB, sends xy to the product of it with the matrix AB, BA. That turns out to be a rotation in this story. But we have to sort of interpret reflection and rotation correctly in the red geometry. And that involves a bit of relativistic thinking. We're going to have to look at essentially what are called Lorentz boosts. That's what's happening here. So we're going to touch base with a little bit of relativistic interpretation in understanding what these things do. But these are the formulas, and you can check relatively easily, just the way I did for the blue one, that they are in fact isometries for the red dot product, where the matrix M is 1, 0, 0, minus 1. And finally, let's look at the grounded green isometries. So the green geometry is another relativistic geometry, a sort of a rotated version of the red one, where the circles are now hyperbolas that look like this, or perhaps like this. And here is the kind of formula. This is the formula for the quadratic form, 2xy. So this would be the equation of the circle of quadrants 2. In other words, equation xy equals 1. So it's a hyperbola with equation y equals 1 over x, and passes through the point 1, 1, and also the point minus 1, minus 1. And then there's a corresponding hyperbola with quadrants minus 2, whose equation is y times x equals minus 1. Okay, so what we're interested in are isometries in this story, and it's a little bit similar, but it's also a little bit different. So we're not in possession of the points 1, 0 and 0, 1 anymore. They're not really, well, they're there, but they're null vectors. They're quadrants from the origin to 0, so they're not so convenient to use in this case. And it's actually more convenient to use the points 1, 1 and say minus 1, 1. So minus 1, 1 would be up there. Now, if we look at the image of 1, 1, okay, that's a quadrants of 2 from the origin, and it's got to be sent to another point, AB, on that same green circle. So there's the point AB. I pictured it on the same circle as the original one. So AB has the property that it lies on this. In other words, that A times B is equal to 1. So there it is somewhere there. And then the possibilities for where minus 1, 1 go, well, that is going to go to also a point on the circle that it's on, but it's got to be a point that's perpendicular to the point AB that we're talking about. Now, perpendicularity in the green geometry corresponds to reflection in either the horizontal or vertical axes, ordinary Euclidean reflection. So the reflection of AB is A minus B, and the reflection on here would be minus AB. So this vector is perpendicular to that one and also to this one. So those are the two possibilities for where minus 1, 1 goes. And then you have to think a little bit about how to interpret this, or how to cook up matrices that accomplish this task. So here's what they are. Matrix 0, B, A, 0. If you multiply this by 1, 1, you get A, B. And if you multiply it by minus 1, 1, you get A minus B. And here, if you multiply by 1, 1, you get AB. And if you multiply by minus 1, 1, you get minus AB, which is that case there. These are, in some sense, a little bit simpler, aren't they? There's something a little bit simpler in the green geometry. That's sort of a common feature of things. And it turns out this has some kind of interpretation as a reflection, and this has an interpretation as a rotation. So in our next video, we want to investigate a little bit further the group structure that's underlying here, the multiplication that we can have with isometries of a given kind. So the blue isometries will form a nice little group, the red ones will form a nice little group, the green ones will form a nice little group. And it turns out that there's similarities but also a little bit of differences. And it turns out there's also some sort of subtle interaction between these three groups, which is also sort of interesting. So I hope you'll join me for that. I'm J Wildberger. Thanks for listening.